This is a production of the Chemical Education Material Study.
Crystals are among the most prized of objects. For centuries, people have used crystals to express and enhance rank. Crystals are hard to exceed in terms of natural beauty and indestructibility. Crystals are also the source of much scientific data on atomic size, shape, packing, and bond formation. For example, we have found that atoms, like oranges and other large objects, can pack together with flat surfaces and straight edges. And like the oranges, atoms can leave holes. These can accept smaller atoms. How do we get this information on size? After all, aren't atoms invisibly small? But first, we go to black and white. Reason? Color is not a factor at the atomic level, as Professor Campbell will show.
This is a crystal, a quartz crystal. Most solid substances are crystalline. Crystals are usually rigid and difficult to deform. They have flat faces and straight, sharp edges which meet at definite angles. Furthermore, each crystal of a given substance has the same faces, edges, and corners as every other crystal of that substance. For example, all crystals of sodium chloride have this 90-degree angle. Even this table salt.
Are these constant factors related to atomic packing? Probably, because regardless of size, sodium chloride crystals have 90-degree corner angles, and all quartz crystals show this 120-degree angle, suggesting a different packing.
Each crystal has its own set of characteristic angles. Furthermore, we can take a straight edge, place it parallel to one of the crystal faces, and tap it. Two crystals form. Each new crystal of sodium chloride has the same faces, edges, and corners as the original crystal. We can repeat this process. New crystal faces form each time cleavage occurs. What about this substance? It has flat sides, sharp edges, and corners. Is it also crystalline? Let's try cleaving it. The material fractures. Curved faces are formed, not like the original flat sides. Materials that form curved faces are called glasses. Glasses fracture. They do not cleave. We can observe another distinction between crystals and glasses by heating them. First, crystals. When crystals are heated, they suddenly melt at a sharply defined temperature. As a glass warms, it loses its rigidity slowly over a wide temperature range. We can explain the cleavage and melting differences between crystals and glasses in terms of structural models. Both crystals and glasses owe their rigidity to the fact that their atoms are held tightly in certain positions. You have learned elsewhere that the atoms in crystals are arranged in specific and repeating positions in space, and that the planar surfaces and characteristic angles reflect the regular arrangement of atoms, which are repeated throughout the crystal. When we cleave a crystal, like this, splitting occurs between the atoms. Plane surfaces form because the atoms are arranged in planes. By contrast, in a glass, the atoms are not arranged in highly ordered positions. Splitting must still occur between the atoms. But since they are not arranged in planes, curved rather than planar surfaces form. Now consider melting. Since the atoms are not in highly ordered positions, the bond strengths vary. Upon heating, the bonds break at various temperatures. Glasses soften over a temperature range. With crystals, all of the bonds are identical. Upon heating, all break at the same temperature. Crystals have a sharp melting point. So these properties of characteristic faces, edges, and angles, regular cleavage, and sharp melting temperature reinforce our belief in the highly ordered structure of atoms in crystals. But how do we determine the actual arrangement of atoms and the distances between them in an unknown substance? Let's consider interatomic distances first. That is, the distance between the center of one atom and its neighbors. This is a mole of copper. It is a cube approximately 2 centimeters along each edge. The mole of copper contains 6 times 10 to the 23rd atoms, or approximately 10 to the 24th atoms. The number of atoms along each edge of the cube would be the cube root of 10 to the 24th, or 10 to the 8th atoms. If there are 10 to the 8th atoms along each edge, the distance per atom will be approximately 2 times 10 to the minus 8 centimeters per atom. This is the interatomic distance. Now we know we cannot see individual atoms with visible light. Let's see why this is so. We can create effects with water waves which will allow us to understand the problems. Here we have a translucent screen on which we can project motion pictures of waves traveling over a water surface. Just as the water waves pass across our motion picture screen, so we can think of light as a wave motion traveling through space.
We place a thin nail so its point protrudes through the surface. The waves are almost unaffected. In the same way, ocean waves are very little disturbed when they pass a mooring post small compared to the wavelength. Let's try a thicker object. This is a machine bolt. Its diameter is comparable to the wavelength. Now we note the waves are appreciably disturbed, as are those at the stern of a ship. This type of disturbance is called diffraction. Diffraction allows us to detect or see objects in terms of changes in the wave pattern. Clearly, diffraction depends on wavelength. Scientists have found that the size of atoms, about 10 to the minus 8 centimeters, is too small to diffract visible light. But near the beginning of the 20th century, X-rays of wavelength 10 to the minus 8 centimeters were discovered. Scientists immediately tried X-ray diffraction by crystals.
We can generate X-rays in this tube. These metal shields absorb the rays generated in our tube, except those which pass through these slits. The sample, in our case a crystal of sodium chloride, is mounted on a stage which can be rotated. Since our eyes cannot see X radiation, we use these fluorescent screens. They emit visible light wherever they are struck by X-rays. Let's turn on the X-rays. Incidentally, the hum you hear comes from this equipment. As I turn up the voltage, an X-ray beam is formed. I'll turn down the room lights. At this setting, the beam of X-rays just misses the crystal and strikes the fluorescent screen directly. Now we rotate the crystal slowly so the X-rays strike it at various angles. The radiation is now absorbed in the sample. No X-rays reach the fluorescent screen. Here's something. Let's stop the rotation. At this setting, the fluorescent screen glows. We say that diffraction of X-rays is occurring. Rotating once more, the diffraction disappears. But here, diffraction again takes place. These lines are usually recorded photographically. We have turned off the X-rays and replaced the fluorescent screen with such a photograph. It includes the arc we've already scanned and goes beyond it. Notice that diffraction occurs only at certain positions. How are these diffraction patterns related to the crystal structure? Here is an array of pegs in 2 dimensions, which might resemble the arrangement of atoms in a crystal. We place the array in the ripple tank.
Note that the peg array is similar to the atomic array in a crystal. We'll call the interpeg distance d. We use a wavelength which matches the peg spacing of d, but only general scattering occurs. You will recall when we rotated crystals in an X-ray machine, diffraction occurred only at certain angles. This suggests we try a new setting for our array. We mark the position, then make a change. At this setting, waves emerge in this way. Diffraction occurs in this direction. At this setting, we notice only general scattering. We rotate the crystal further, and now notice diffraction patterns here. The waves strike the crystal from this direction and emerge in this. If we place the edge of a protractor along this row of pegs, we find that the wave angle of incidence and angle of reflection are equal. Is this always true? We return to our original diffraction pattern and again set the angles. Now we place the edge of the protractor along this row of pegs. Again, the angle of incidence and the angle of reflection are equal. Diffraction always occurs from rows, such that the angle of incidence equals the angle of reflection. We'll call that angle theta. Now, suppose we keep the array of pegs stationary and alter the wavelength. We'll call the wavelength lambda. The diffraction pattern disappears. There is some general scattering. We continue to decrease the wavelength, and a new diffraction pattern appears. Notice that the wavelengths of the diffracted waves are the same as the wavelengths of the incident waves. As each experiment shows, diffraction occurs at particular combinations of wavelength lambda, angle theta, and distance d.
Again, the angle of incidence equals the angle of reflection. In general, diffraction is described by the Bragg equation. D equals n lambda over 2 sine theta. In our experiments from now on, n will be unity. And therefore, we will use the expression d equals lambda over 2 sine theta. Here, lambda represents the wavelength. In this case, 2.8 centimeters with an uncertainty of 1/10 of a centimeter. Theta represents the angle of incidence of the waves upon the rows of diffracting pegs, and d equals the distance between adjacent rows of pegs. Imagine this is our sodium chloride crystal. A knowledge of the X-ray wavelength, lambda, the angle of incidence theta, would allow us to calculate the distance d between the rows of atoms. And it is clear that any array will have many rows which will satisfy the Bragg condition. D equals lambda over 2 sine theta. Of course, in a real crystal, we cannot see the atoms.
So how about some hide and seek with an array of pegs hidden from view? Only the diffraction effects will be visible. At this setting, there is no diffraction. We shall assume that the distance d in the hidden array is a few centimeters. Thus, the wavelength of 2.8 centimeters, which we have been using, will be appropriate, and we can expect diffraction at several angles.
Watch this point. It indicates the position of the hidden array. There's a change, and now we see diffraction waves coming out in this direction. Let's keep track of our findings. The incident waves come in this direction, and the reflected waves leave in this direction. Since the angle of incidence always equals the angle of reflection, there must be a row of pegs parallel to this line. Let's mark it. The angle of incidence is 34 degrees plus or minus 1 degree. Let's calculate d. We can calculate the distance using the Bragg formula. Lambda equals 2.8 centimeters, and the sine of 34 degrees is 0.56, or d equals 2.5 centimeters. So let's mark off our 2.5 centimeters distance. Draw a set of parallel lines which will represent the pegs in the hidden array. Here's a new setting. No diffraction. Another setting. Diffraction recurs. Now we must rotate our record in order to match the hidden array. The wavelength is still 2.8 centimeters. The new angle of incidence is 42 degrees. We now have all the data necessary to calculate a possible array. There will be a row of pegs parallel to this line. Let's calculate d. Lambda is still 2.8 centimeters. The sine of 42 degrees is 0.67, or d equals 2.1 centimeters. Using our value of 2.1 centimeters, we draw additional lines which will represent further rows of pegs in the hidden array. But where are the pegs? Actually, the pegs could be in many positions on these rows. But we shall make the simplifying assumption that the same pegs determine the positions of both sets of rows. If this assumption is correct, the arrangement of these intersections will be the same as the arrangement in the array of pegs. Let's look. They are.
In other cases, we would have to do more experiments and determine the positions of further rows. The Bragg equation works. We can determine atomic distances and arrangements. Contemporary X-ray diffraction is highly computerized, though interpretation is still based on the Bragg equation. An even more direct view of surface atoms can be obtained by a method called electron tunneling. The specimen to be studied, in this case graphite, is mounted on this block. In the tunneling instrument, the specimen is positioned several atomic diameters from a tiny tungsten point. The point is electrically charged, and a voltage applied so that electrons will leave the tip and strike the specimen. The tungsten point is moved to scan an area of about 100 atoms. During scanning, a computer keeps the current constant by keeping the surface to point distance constant. Because surface atoms are roughly spherical, no surface is truly flat. The point position data are fed into the computer as scanning proceeds, producing this video image of the surface. Each bright spot represents an atom. This scan of the graphite surface produces a hexagonal pattern which matches the hexagonal structure of graphite obtained from X-ray diffraction. We have used a simple structure, graphite, but the scanning tunnel microscope is providing much data on far more complicated surfaces. Diffraction patterns related to the Bragg equation provide data for three-dimensional structures. Tunneling microscopes provide similar data on surfaces. So we can enjoy crystals for their beauty, but also for the insight they give us into the molecular world of chemistry.